Okay, perfect. All right, great. Some quick slideshow and we can dive in. All right, hi everyone. My name is Mark Kurtz. I direct the machine learning team for Neural Magic. At Neural Magic, what we specialize on is making deep learning more accessible, more performant, and easier to use. And we do this through sparsity and sparsification, along with a lot of engineering that goes around that. So there's a lot that we do in terms of doing our own research as well as productizing research. So if there's anything that you'd like to, any questions you have or anything like that, feel free to contact me on LinkedIn. More than happy to dive in. And also I share quite a bit on there in terms of machine learning kind of results, new state-of-the-art results, research papers, and an understanding. Additionally, feel free to check out our GitHub at github.com/neuralmagic. And this is where we have all of our code, everything that you can use to create your own sparse networks and to play around with deep learning. And so for this session, we'll be a little bit more hands-on. I'm going to go through some high level, well, a little bit more in detail than what I did yesterday around sparsity approaches and the algorithms that go behind them. And then additionally, once we get through that, we'll actually dive into some live examples for running some sparse networks and showing how to create them. So diving to sparsification, just kind of, generally we should always sparsify or optimize our models before deployment. And this is just because if we're not, we're leaving free performance on the table. And whenever I talk about sparsification, I mean any kind of essentially model optimization, where it could be anything from simple quantization, and we'll go through all these later, but simple quantization to more advanced pruning techniques, things like that. Generally, there's always something we can do to optimize just a baseline neural network and be able to get more performance. And even just taking it out of PyTorch and TensorFlow and putting it into a inference engine that's purposely built for performance can give significant speed ups. And this is what you see whenever you see, like, for GPUs, TensorRT versus just PyTorch GPU. These runs, PyTorch GPU runs significantly slower. You can get probably at least a 3x performance increase just by converting your model into a TensorRT graph and running it from there. Additionally, same thing happens on CPUs. So going from PyTorch CPU or TensorFlow CPU into deep sparse, for example, our inference engine, or even Onyx runtime, will give you usually a 2 or 3x increase in performance. That's just because these are optimized to specifically for the hardware that you're deploying on. And to what extent and which methods to use, it can vary. For example, if you don't have training resources or time to iterate, meaning that maybe you need to get the project out very quickly, or you just don't have GPUs or even access to the original training scheme that happened for the model, then quantization is always a safe bet. This can generally be applied in one shot, and we'll go through this later, but it's usually always a safe bet to at least quantize your model. And if you do have time to iterate and your hardware supports it, then pruning plus quantization is a great option. Is going to get even more performance off the table, really optimize that model further, and remove the redundancies that are inherent in these neural networks. And finally, if you do have time to iterate and want maximum performance, you can iterate through distillation of a smaller model plus pruning plus quantization. And for those that may have seen, we had some news that went out I think 2 months back for the MLPerf results. MLPerf is it's an open performance benchmark for neural networks. And we submitted to that. And what we were able to do is actually take a BERT large model, just a baseline model. We were actually able to increase it over 175 times in performance by doing this last state. It took a little bit to get to an end model that would do that. But overall, reasonably within reach of most people. And we were able to actually keep the same accuracy and hit 175x in improvements. So feel free to check those out. Just look up MLPerf Neural Magic and you'll see all those results, as well as all the code that went behind that. Diving into pruning. So as a refresher, pruning is going to remove the unused connections, right? So we're looking at this fully connected network over here. We're going to come through and remove the weights that are connecting these nodes, the ones that don't matter. So we end up with a not so fully connected network afterwards. This results in sparse models with fewer parameters and less compute and storage is needed for the model, right? So this way we can actually get performance, provide the hardware supports, and we'll go through what that hardware support looks like. So for unstructured or semi-structured pruning, definitely recommend this if hardware supports it as a pathway to go as compared to structured, which we'll go through in a second. This is supported on CPUs by Neural Magic, both through unstructured and 4-block. So I'm going to go into the differences of these a little bit here. So unstructured is what we're doing here, where it just looks like a random assortment of weights removed. Whenever we do semi-structured, we're actually blocking in groups of 4. So for example, what we might do, and it depends on the network how you block, but whenever we're looking at this fully connected network at the top, and hopefully everybody can see my mouse. Let me know if you can. When we're looking at this network at the top, well, for 4-block, we're going to remove the first 4 connections, and then. Oh, sorry, I think I hear somebody come through. But yeah, so we're going to remove the first 4 connections in a group, and then we're not going to remove the next 4. So this just means that we're going to group the connections together in blocks of 4. Either we keep all 4 or we remove all 4. And the reason why we have 4-block on here is actually because of some hardware constraints on the CPU side. Specifically with Intel, they have the VNNI instruction set, and what that takes in, it's a specialized instruction set for quantized models to get even further performance speed up. And what it takes in is 4 int8 models, or 4 int8 numbers, and then outputs its FP32. So it's a requirement from the instruction set. So that's why we do 4-block whenever we're doing semi-structured, sparse plus quantized models. And I can add a little bit of complexity to the pruning process. This is also why at Neural Magic we're working on simplifying that. So you can just run unstructured everywhere, and we're actually going to do a lot of complicated optimizations under the scene to take advantage of the 4-block, but without you having to inherently do that. So unstructured 4-block is what you're looking at for support on CPUs. Looking at GPUs, the Ampere GPUs can give some speed up depending on the model. So this is where we're looking at, for example, BERT Large. They have a decent result on. They get about 20% speed up on BERT Large, and this is where they're doing a 2-4 block. So every 4 weights that we're going to connect, 1, 2, 3, 4 up here, we're going to get rid of any 2 of those, and that's the restriction that they have on just from the hardware side. So this, what they say is that at least their performance benchmark go for certain matrices, that they're able to get a 2x speed up on those. In reality, generally the neural networks are not shaped correctly to be able to take advantage of that. BERT Large is actually one of the only models that we've been able to realize speed up on the GPUs for that. For example, image classification object detection models, it actually doesn't, the TensorRT libraries don't actually enable sparsity for those currently. So we're looking forward to further support from NVIDIA on that side. But currently, so if you have a large language model, 2-4 pruning works and can get you further speed up on GPUs. And then FPGAs. So this is supported by Moffat AI and others, right? So where we have more of the custom circuit boards and custom setups rather than CPUs or GPUs. And generally they'll take in unstructured. They can get really, really good speed up on these if there's high enough sparsity. So this means they generally need to see like 90–95%, actually more than 95% to see significant speed up, but they work pretty well. And that's where we're looking at unstructured generally for FPGAs. Diving into structured pruning, as I showed yesterday, this is where instead of removing these connections, we're going to remove the channels. We're going to remove these nodes. So going from this fully connected network, rather than removing any connections over here, we're just going to remove 1, 2, 3 nodes here, and it gets rid of all the connections. And if you'd like to dive into that a little bit more, I have more in the talk that I gave yesterday, which will hopefully be available. The good news is that it works everywhere. And the reason why is because we're actually changing the structure of the matrices underlying these neural networks. So this means that if you had, a 8 by 8x4 tensor or matrix, and we reduce it to a 4x4 matrix, anything's going to run that faster, right? We've reduced the amount of memory that needs to be transferred into the compute units to run it, as well as reducing the amount of compute that has to run. So structured pruning works everywhere. The big thing is that it's just harder to do and to recover with it. Oh, I apologize. Not sure what's happened with my slides here, but diving into the sparsification equations. So we have magnitude pruning at the top here, which is where we're going to take in a weight and we're going to set a threshold on it. So we're going to keep the weight if it's greater than some threshold, or we're going to set it to 0 if it's less than that threshold. So what this looks like in practice is that whenever we're going to apply pruning, we're generally going to look to apply it at some set sparsity level, whether it's 10%, 20%, 50%, or higher, depending on how much we're trying to get to. And generally, we'll try and get to like 90%. But we're going to look at the entire matrix of weights that are available to us, figure out what threshold we need to set to reach 90% sparsity, and then we plug that threshold in and then apply that across the weights, right? So we're going to set all weights that are less than or equal to that threshold to 0, and that means that if our sparsity target was 90%, we're only going to end up with 10% of the weights above that threshold, and that's what we keep. So it's a pretty simple algorithm for magnitude pruning to go through. Movement pruning, on the other hand, is a little bit more complicated. And what this is actually looking at is it's looking at the gradient of the weights as respect to the loss, as well as the weights themselves, and multiplying those together. So, and then we're setting a threshold based on this. This ends up being the threshold that we want to target. So rather than looking at just the weights and thresholding based on just the weight value, we're actually going to threshold based on this equation here. So the end effect happens to be, because these have to be matching and sign to be pushed away from 0. Ultimately, any weight that is trending towards 0, meaning that it's a positive, it has a positive weight, but it has a negative weight update, meaning it's getting pulled back to 0, or it's a negative weight and it has a positive weight, meaning it's trending back to 0. We're going to remove those. So anything that's trending negative across this line is what we're going to remove. So what this has an effect of, and the intuition behind movement pruning, was that as you're training, the weights that are trending towards 0, as the gradient information is telling you, is what you're going to be removing. Because those are the weights that the inherent regularization that comes with SGD, as well as the regularization that happens on these networks, that is telling us that we should remove that weight. So that's all that this one is doing. And in practice, it works decently well. Overall, though, magnitude pruning, if you let it run for long enough, it'll generally beat out movement pruning. Movement pruning, you can think of it as just a quick heuristic that allows you to prune faster. But if you generally, for pretty much any equation in here, magnitude pruning, if you just let it run for long enough, it's going to eventually beat those out. And that's just because SGD really has that self-regularizing effect. And so if you let it regularize for long enough, then magnitude pruning typically works out well. The one exception to that, though, is actually second order, which is Wood-Fisher pruning. And there's some derivatives on this that we push out in papers. Wood-Fisher was invented by our principal research scientist at NeuralMagic. And that's a second order approach to pruning these networks. And what I mean by that is it's calculating the Hessian. So it's looking at the effect of each weight on the loss, trying to create an approximate for what that effect is going to be. So it's going to not only look at the first order, but it's going to create a Hessian matrix of the weight with respect to the loss function. And what we can do with that then is actually use that Hessian to not only figure out which weights are least likely to affect the loss, but additionally, for the weights that we removed, because we have the Hessian information, we can actually update all the other weights that we haven't removed to try and make up for the fact that we removed those weights. So it actually ends up being a weight update, a little bit like optimization of stochastic gradient descent and optimization of those weights. So that's a big benefit that you get out of that. It is quite a bit more expensive than magnitude pruning and movement pruning to apply, but the result is a much better algorithm that allows you to prune faster. We can actually, something for magnitude pruning that would take maybe 30 epochs, for example, whenever we're looking at training an NLP model with BERT. Something that takes 30 epochs to prune only takes 5 with Woodfisher. So it's a significant reduction in the time. And Woodfisher is also where we're working around our one-shot algorithms. Because as I mentioned, we're actually updating the weights as we're removing. So it works really well for one shot. And this is where we're not retraining the model. And I'll go through all of those methods a little bit as well. Okay, great. From the quantization side, so quantization removes the unused precision in the network, right? So weights and activations generally quantize from floating point 32 to N/8 with recovery on these. It's a 4x reduction in size, memory, and you can get further gains in compute depending on the hardware. And some advanced techniques can push to N4 and N2. So diving into the hardware a little bit, we have N/8 static quantization, which is supported nearly everywhere. So on CPUs, Neural Magic R deep sparse engine fully supports static quantization at N/8. And to go through the differences between static and dynamic, definitely check out the talk from yesterday. But for today, we're just going to focus on static because that's generally where you're going to get performance, and it's always pretty much always recommended. So looking at N/8 static quantization, again, this is supported nearly everywhere. On CPUs, you'll get it with deep sparse. Depending on the chipset that you're using with CPUs, will could give you better or worse performance. An older Intel or AMD chip are going to have worse speed up in relation to what happens with just the FP32 baseline. This is because they only had AVX2 vector instruction sets. This is where we're taking 256 bits and being able to run those all at once on the register. But newer Intel chips and AMD chips have not only AVX512, but they're also starting to get VNNI. And VNNI, as I said earlier, is the specific instruction set on CPUs that gives a significant performance speed up for running N/8 numbers. It's a vector instruction specifically for N/8, specifically for quantized neural networks. And that's able to get significant speed up actually by using that. And to the point of 4x is pretty common, at least for the compute speed up. But you're going to have memory slowdowns and things like that with quantization. So on GPUs, we have full support with NVIDIA CUDA and TensorRT and others. TensorRT being the more performant version of CUDA and leveraging the CUDA cores that NVIDIA started building into their GPUs specifically for quantization. So it supports N/8 and you can get really good speed up there. They actually, depending on what the exact quantization setup is, they actually get better than 4x for compute speed up. You're not going to realize that across the entire network, but at least for a localized matrix multiply, you can get better than 4x. One note is that the supported graph for the software and hardware can be tricky to generate. All these engines are very specific to a certain graph for the model. And when I mean graph, I mean whenever we export this, right? So this is the graph that we're looking at. And whenever we quantize this, there are different operators that can get injected to be able to do that. And TensorRT has their own graph language. For example, for quantized networks, deep sparse, we use Onyx, and we have a specific graph language within Onyx or a specific static representation of the model within Onyx. And then Onyx Runtime and others will expect those. So this is where the software built around all of this becomes really important because we need consistency with these graphs because small changes in the graph can lead to an entire rejection of not running a quantized network. And this is what we've seen trying to actually generate faster TensorRT graphs for NVIDIA. It becomes much, you can lose 20, maybe 50% performance with just small portions of the graph not actually getting compiled into the correct TensorRT representation that they did performance optimizations around, they meaning NVIDIA. One other note is that NVIDIA does support lower quantization levels, such as N4. It's much harder to do for activations though, and actually recover. Weights are generally pretty easy to quantize down to a lower level like N4 or N2, but it's really hard for activations. And this is where we get into, we need more complicated algorithms, which generally limits hardware support for speed up. So the most complicated that NVIDIA is able to support is going to be channel-wise quantization. So looking at every single channel across a layer, where we get into convolutional neural networks and things like that, they're going to support a different quantization band for each of these channels, and that gives you some flexibility overall because you don't have a single quantization band applying to the entire network. And ideally, this gives you well, it does give you more flexibility, but ideally it gives you the right flexibility so that some channels can be quantized more, other channels can't be quantized as much, depending on how the model is trained. So that's where they can get down to some lower levels on quantization with Ent4. But actually, the most efficient ones that do get down to really low quantization levels are going to do things like banded quantization and others. This is where instead of taking looking at your entire distribution as your input, which you're taking as FP32, and you're trying to convert that into Ent8, you're rather than taking that entire thing and generating a single number and linearly doing that interpolation across everything, you're going to do bands across that. And this is because the actual activation matrix range, which actually, let me just pull one up real fast. If I can get, there we go. All right, let me see. Let's see if we can pull up just a distribution image real fast. Yeah, there we go. Okay, so whenever we're looking at these weight distributions, we're going to be quantizing into this. And what we end up with is actually a pretty normal looking statistical distribution for these. So typically you'll just do a linear interpolation of this down into a quantized band. But what people have realized is that you want to put more precision in the middle, right? Because you have more of your values with this distribution in the middle here. And towards the tail, you can actually represent that with less bits. So since you only have Ent8, you have 8 bits, you want to put most of your precision in the middle. And so they'll generate bands around this and then have different rules for those bands. All right, great. Sorry, and then I think I just saw a message come in. Let's see where it went. There we go. So we had, does the engine take advantage of Intel VNI instructions and MMA features on IBM Power Architecture, VNI on Intel chips? So yeah. So whenever we're looking at the Sparse engine, taking advantage of VNI on the Intel chips, and most engines will do this whenever you're looking at a CPU engine. For the MMA features on the IBM Power Architecture, we have not optimized for that, and I'm actually unsure of any engines that are available for that. I'm sure there are, but it's something that I'm not positive on. All right, great. So we ran through quantization for hardware support, and then distillation. So we talked over yesterday. Distillation guides the training process to enable better accuracy in smaller models. So this means that a teacher network, this bigger network here, is going to be used to generate the correct outputs for the student to learn from. So same input goes into the teacher and the student, and then we're going to use the outputs from the teacher to reflect on the loss function for a student, so that we can tell the student essentially what the output distribution should look like, where the larger model is going to be more accurate, right? So we're trying to force a smaller model to learn the complex relationships that a larger model has. So this generally has the effect of smoothing and correcting the loss surface, right? So we have something that's understanding, you can think of it as kind of embedding from higher dimensional space into a lower one, where the lower one is something that the more compressed model can understand. So for hardware support, this is going to work everywhere. Smaller models are structured modifications. So not looking at this one, but if we were to have generally in traditional distillation, what you'll do is either use an ensemble of different models that you may have trained for different hyperparameters and things like that. Use an ensemble, and then the output from that entire ensemble is used to then retrain the model. Retrain just one version of the model, so you don't have to run 10 different models for every inference. But additionally, you can use it where you can cut down significantly on the weights and on the layers, for example, and be able to get a smaller model and get it to a higher accuracy. Unstructured and for quantize. So sparse and quantized models, they're going to follow the previous rules that we just went through. If you have hardware support, then it's definitely a great thing to do in terms of distillation, and generally will always get you better results. And there's a little bit of a caveat on there, which is what we're going to go through. Works very well for NLP models. This is something that was found with Distilbert. I think this was back in 2018. Might have been a little bit after that, but sometime around then. Distillation just works very well for NLP models, where the typical thing is that you'll remove a lot of the layers from your NLP model, and then you have a large model that's guiding that. So generally, always use it. It also works especially well for sparsity. So whenever we're looking at sparsity results, where we might have had 60% pruning possible, and this is actually right around where the state of the art was before us, along with Hugging Face, started pushing more research into the space for pruning BERT and other models. Generally, you'll be able to get to about 50%, maybe 60% before you start dropping in accuracy. And this is not enough sparsity to really be able to leverage for significant speedups. So what we did is added in distillation, where you keep the model size the same, take your dense network before you pruned it and you've trained it, and then you're just going to distill while you're pruning it. So you keep a copy of it, use that, and say that you want to match the dense representation. And this actually allows you to get all the way up to 90–95% sparsity. So a significant increase in the amount of the network that you can get rid of just from utilizing distillation. It doesn't work as well for computer vision models. This is something that we haven't seen even with optimizations like pruning and quantization, or even distilling into smaller models. It doesn't work anywhere near as well as the results that you see on NLP. There's not a lot of intuition for why currently, but we do actually have some new results that are going to be coming out soon for layer-wise distillation with object detection networks, where this actually significantly helps out. So it seems like rather than, and to dive into layer-wise, rather than just distilling on the output here, what we're going to do is at every activation output, we're going to add a distillation loss on those. So essentially what we're telling the model to do is match the original dense representation at every layer, right? Match the output at every layer. This actually helps out significantly. I can't go into the results too much because we haven't finalized them and haven't published them, but it is a really interesting result. And then diving into the application methods. So we have post-training one-shot. Use this generally when you're limited on time or resources. And this is where we're going to go through, and rather than doing all the retraining I was talking about in the iterative pruning, things like that, we're just going to take a trained model and apply it at the very end. And we can use this whenever we either don't have access to the original training scheme, or we don't have the resources to run retraining. It's also much faster, so that's why we say when you're limited on time. It's very simple to apply, but may not get good results. Generally, we're limited to a 4x speed up with deep sparse and other engines, somewhere around there. This is for our newest research, which we haven't pushed out as into the code base yet. So stay tuned for that. But yeah, generally we can get to around 4x speed up with one shot. So think, in 10 minutes, just give the model to an algorithm. It's going to go through and do that Wood-Fisher algorithm I was talking about earlier to be able to prune the model and iterate through just with a small sample of data. And then it works pretty much the same way for quantization. Training aware. We're going to want to use this when we have time and resources and need the absolute best performance, right? So this is where we're taking the dense converged model. We're going to iteratively prune away at it as we're going through. It's harder to apply, but we will get better results for this. And the spread bars, we can actually get to above 40 times faster with deep sparse. So this is really, really good performance whenever we do sparsity plus, so pruning plus distillation plus quantization, we can get to 40x faster. And these are the results that we published for MLPerf. And sparse transfer, we want to use this where when we want to quickly iterate, or we're already fine tuning. So for example, if you have an NLP data set that you're just using the pre-trained BERT for, and you're just fine tuning it onto that data set, I shouldn't say just, because that's a big challenge in itself. You can pretty much just swap in a sparse version of that architecture, and it's going to work exactly the same. So you can keep everything that you're doing the same. You don't have to iterate through hyperparameters around how to sparsify the model. You just plug it in, use distillation, and it works really well. Okay, great. All right, and then just diving into the tools that we're going to be going through. So I went through this yesterday. I won't focus too much, but the big concept for sparsifying these models is recipes. So it's where we're defining the algorithms and the hyperparams in YAML rather than trying to create a code base which isn't flexible. So we create a YAML language which is just made up of modifiers, where you can say, hey, I want to prune the model, start at this epoch, end at this epoch when we're doing training aware, and iteratively prune all the way up to 90% while you're doing that. Sparsu, this is where we have all of our state-of-the-art recipes for sparsifying models. So you can take a look through there, sparsu.neuromagic.com. You can take a look through there. We have all the recipes that we've used internally pushed up there. So you can take a look at what those recipes actually look like. And we'll go through some example ones in a little bit. We also have pre-sparsified models for sparse transfer learning. So whether it's object detection, image classification, NLP, or other use cases, we have sparse models pushed up so you can just fine tune onto your data set without having to do any of the further optimizations. And if you're doing a project, I definitely recommend starting out with sparse transfer learning to try and get some quick results. SparseML, which we'll go through, supports many of the state-of-the-art algorithms and integrations that I just went through. And it's only a few lines of code generally to apply a recipe, and we'll go through some examples on how to do that. And then modifiers that are contained in that recipe modify pretty much any part of the training graph. It also supports one-shot, but we haven't pushed as much behind that yet. That's coming out soon. But the modifiers are going to essentially modify any part of the training graph, what we do, and we'll go through this. But what we do is we take over the training process, and then that way we can inject the sparsification code at runtime so that you don't have to worry about building out all this code to be able to do it. It's open source and growing. And then Deep Sparse, which we've gone through, is our the fastest CPU inference engine, and it utilizes Sparsity. So it's able to get speed up from these sparse networks. It's free to use for community and research, so feel free to try it out and try and get better performance. So let's go ahead and dive into some demos. And what I'm going to stick to is actually our docs website. We just pushed this up, revamped to this on, actually, where did it go out? It went out yesterday, actually. So new results here. I want to run through this just so that everyone knows where to come back and reference these if you're trying things out. So what we'll start off with is try a model. And under our try model, what we're doing is trying it out to see what our performance is going to look like for models that we've already pushed up to Sparsu. So we can actually use these sparsified models and be able to run these. So we'll look at what this looks like. So what we have here is a pipeline, and we're going to create a text classification pipeline. We're going to use a model from the Sparsu. These are called Sparsu stubs here. And we're going to use that to create a pipeline and then run inference with it. So for example, what's shown here is that it says fun for adults and children and fun for only children. So we're running our text classification pipeline. This is one that was trained on NNLI. And it's a natural language corpus. And what it's doing is it's trying to tell whether or not the sentences are similar or not. So we have fun for adults and children, fun for only children. It tells us that those two sentences are a contradiction. So we're going to go ahead and run this. Go over to our terminal. All right, and then let's jump into Python. And let me actually copy these in. Well, yeah, I don't think I'm gonna be able to do that. So we'll go ahead and import a pipeline from Deep Sparse. It's going to actually download a bunch of the requirements that it needs to be able to run the Hugging Face one. So after this gets done, I'm going to kill it and restart it so we don't have all this noise in the way. But the good thing is that you just run pip install Deep Sparse, and then you can run any of this code, and it'll pre-install for you. All right, so what it did is it installed deepsparse.transformers. We build on top of Hugging Face transformers to run all of these. And now it's downloading the model, and now it's compiling the model. So let's try and run that again. Let me get out of here. Oops. And clear the screen. All right, so let's try that again. And let's run that example. So we imported our pipeline. We created that classification pipeline from that model that was on model available on the Sparsu. And now we've created that pipeline. It's running on the server that I have this on here. And so you can run this locally. It works on any Linux setup. So feel free to do pip install deep sparse, and then you can run this exact code. So what we're doing is running this inference, and we ran it through our pipeline. So we gave it 2 sentences to see if they are contradictions or the same or not. So, and as we see, we get a contradiction and gives us a confidence score on that. Another fun example is zero shot. So with the MNLI data set, what we can actually do is leverage the fact that it's looking at contradictions or not to be able to say, is a sentence a certain label, right? So what we're going to do is run a sequence here that says, who are you voting for in 2020? And we're going to run it through and check, is this a politics label? Is this a public health label? Is this related to Europe, for example? And you put any labels that you want in here. All it's doing is leveraging the NLI scheme to be able to say, is a sentence similar to this label or not? So we'll run that through and see what that looks like. Let me see how this and start a new one. Okay, so we imported a pipeline from deep sparse, created one. We told it that we want to create a zero-shot text classification pipeline. Gave it the model from the sparse suit to use. Told it to use a scheme of MNLI, which is the data set that we're training on. And then we have our hypothesis template. So the text is related to blank. This is just what the prompt going into the model is going to be. So for these different labels that we have, we're going to say, who are you voting for in 2020? And for every label, it's going to compare it with this text. So it says this text is related to politics. This text is related to public health. This text is related to Europe, for example. And that way, we don't actually have to train a model at all. We can just use the fact that we have a pre-trained model and do zero shot onto whatever our data set may be. So we have our labels, and you can see our confidence scores coming out. So for politics, it has a very, very high confidence that is politics. It's not as related to Europe, and then even less so to public health. And I definitely agree with that. I don't know if all the stuff going on in politics, definitely think takes away from public health right now. Great. And then one other thing we can do is just look at benchmarking. So whenever we're benchmarking these models, we want to see and make sure that all that time that we put in for sparsifying these models, or will put in to sparsify these models, gives us a faster model. So what we're going to do is start off with a baseline model. This is an unoptimized FP32. It's not pruned, it's not quantized, and it is not distilled. So we're going to run our baseline. This is a Distilbert model, and the MLI model that we're talking through. We're going to run that. Deep Sparse is going to kick off, and it's going to run multiple iterations through this model to see what our average performance is going to look like. So it's creating the Deep Sparse engine, and then it just kicked off the performance. So it's doing a performance measurement for 10 seconds. It's running as many inferences as it can for 10 seconds. All right, so we'll wait for that. That should finish up soon. There we go. So we end up with 143 items per second. So 143 sentences that we can send through within 1 second. Now, what we're going to do is we're going to take our pruned and quantized model and run that through to see if we get a performance difference. So the machine that I'm running on is a C6i instance on AWS. This has both Intel VNI instruction sets as well as AVX512. It's a 24-core machine, so that's why it's running pretty fast. But yeah, so it kicked off that performance measurement. All right, great. And you can see we got 982 items per second, so a significant improvement over the top of what our baseline was. All right. And then additionally, we also have object detection. So if you want to do a quick object detection example, here you can see, and I'm not going to be able to do this, unfortunately, locally, because I cannot transfer the image off that quickly off the server onto mine to render it. But hopefully you'll get the idea. So what we'll do, so we'll copy this, and we're going to just download a general image from the internet. This is just an example image. I'll show you what the example is. All right, so we're going to be classifying on this image. So what we'll do, and let me walk through this before we paste it in. we're going to create our pipeline from deep sparse. We're going to tell it that we want to use a YOLO model, a YOLO task, which means that we're set up for both the pre-processing and post-processing, specifically for YOLO model. YOLO being a very popular object detection model. And what we're going to pull down is our YOLO v5l, which has been pruned and quantized. So we're going to run that through. We can also pass in class names and a model config, which is how you can control what classes it's predicting based on what you train it for, as well as a model config to control things like the confidence threshold, IOU threshold, which you can also pass in here. And then we're just going to run the inference. So we're going to give it the image that we downloaded locally and an IOU threshold and a confidence threshold. These are parameters that we can control to say what our thresholds are for actually printing out a bounding box for it. And then it's going to print out all of our bounding boxes. You can use this actually to then annotate the image or make informed decisions based on the bounding boxes that came out of it. So let's go ahead and run that. All right. Oh, I apologize because I did not install the proper deep source. So what we need to do is install pip deep source YOLO. Oh, pip install deep source YOLO. All right. And that's going to install all of our dependencies that we need to be able to run the YOLO pipeline. Wait for that to finish up. It looks like we're about done. All right, while we're waiting on that, we additionally have some benchmark commands that we can do, which this will give you about a 3.6x speed up for the one that we showed here. All right, perfect. So let's go ahead and run that. No, I don't know why this is working, so I apologize on that. We'll go ahead and exit out of this one. Need to figure out what's going wrong there. But let's go ahead and dive into a custom use case. So for a custom use case, what we can actually set up are different inference pipelines. And this is an example of, so if you create your own sparsified model and it's not a pipeline that we built into deep sparse yet, this shows you how to run through and define a pipeline so you can actually use deep sparse and get all the benefits of the pipeline. So this is showing just a custom task pipeline that you can use, and then creating an image classification pipeline around that. So what we're going to do is define our custom pipeline. We're going to pass in a pre-processing function, which is everything that's going to run before we run through the engine. So this, what this is doing is it's opening the image file, converting it to RGB, running our pre-processed transform, so it's resizing, centering, turning it into a tensor, and then normalizing it based on our means and standard deviations across the average of our data set. And then we're returning back a NumPy array that the deep sparse engine can use. After that's done, it's going to pass all of that information through the deep sparse engine for the model that we have. And then we can also add in post-processing if we'd like as well. Here, we're just going to return the outputs. And what this is going to do is run that custom pipeline and print out our inference. So this gives us our confidence on of what class that model was. All right, great. And then benchmarking, you can just pass in any Onyx model into dSparse.benchmark. So let's go and dive into transferring for a sparsified model. So specifically for NLP text classification, and I don't have a GPU server spun up currently, so we're just going to walk through this one. What we have is the zoo stub. So this is the model that's available on the sparse zoo that we're going to be using. We have it's a BERT-based model, and this is our baseline. So what we're going to do is first create a teacher model for our distillation that we're going to use later to for sparse transfer. So we're going to create our teacher model. All that we're telling it is to output it here. We're going to use our dense BERT baseline to create our teacher model, and then we're just going to use a standard recipe. This is just a standard text classification training recipe, and we'll go through recipes in a few minutes. We're going to give it a few args to pass in, but we're going to train it for SST2. So this is a sentiment analysis data set. All right, and then we have a few other arguments that you can pass in. These are all documented. If you do this command, sparseml.transformers.textClassification --help, then you can run through. So sparseml is installing the CLI, and then we're going to run through create our teacher. After we have our teacher, then we can start transfer learning. So what we're going to do is we're going to take a Dilbert model. So we're going to remove half the layers from the BERT model. That's what Dilbert does. We're going to take our Dilbert model, and we're also going to take a pruned model and one that's ready to be quantized. So we're going to transfer from that model, from this model that's trained on the upstream. So this was pruned on a large corpus, large text corpus. And what we're going to do is tell it to run text classification again. We're going to output it to our sparsified models directory. We're going to use that pre-sparsified Dilbert model to create it. We're going to use a sparse transfer recipe for it. And then we're going to use that teacher that we created. So that teacher helps guide the sparse transfer model to the correct solution. So once we complete that, then we'll have a text classification model that's ready to go. And the final step is exporting to ONNX. So this is the graph format that is very common, and the general open source graph format that works across TensorFlow, PyTorch, and a lot of other engines, and what we use with Deep Sparse. So we're going to export the model to ONNX, and then we can use that ONNX file with the Deep Sparse engine as we went through in the try model section. For CV object detection, because distillation doesn't work as well on CV, we actually don't have to create a teacher for this one. This one just works out of the box. So we're going to use a YOLO v5L model, the same one that we were running before. We're going to take the pruned quantized version, or the pruned version set up for quantization. We're going to then run a sparseml.YOLO v5.train. So we're integrated with Ultralytics YOLO v5 repository for being able to create object detection models. What we're going to do is tell it to use the weights from that YOLO v5 model. We're going to use the recipe for a sparse transfer recipe from that YOLO v5 model. And then we're going to run through and train. There's just a few things around hyperparameters and things like that. We're going to train it on the VOC dataset. So originally it was trained on Cocoa. As you can see from the stub here, it's trained on Cocoa. We're going to run it on the VOC dataset. So we'll just kick that off. And ultimately what we end up with is an output in our output project directory here, YOLO v5L. And what we can do then is use this export command to export to ONNX. And then we're ready to run through the try model section we had earlier. All right, and then finally running through one last thing, sparsifying a model. So this is how we go about actually creating a new sparse model rather than just sparse transfer learning, as we're talking through. So we have pruning and pruning recipes. So what we'll run through is just what one of these recipes actually looks like. So what we define are modifiers to the training graph that we want to apply. We're going to do a global magnitude pruning modifier. This means it's going to do magnitude pruning, and it's going to globally look across all the weights in the model. It's going to start at 5% sparsity, starting at epoch 0, and it's going to get to a final sparsity of 80% at epoch 30. And we're going to prune once an epoch. Underneath, what it's actually doing is a cubic schedule rather than a linear one. So we're going to prune a lot of weights at the beginning and then prune only a few per epoch at the end. And that's just kind of a side note that cubic schedules work really well. Other things that we're going to do is just set up our learning rate. You can define this either through your hyperparameters that you're passing into the training script, but we found it to be easier just to keep these in the recipes, so that way everything is contained. So we're just defining how we're going to be doing the learning rate. And then we have an epoch range modifier, which is going to tell it to run for 50 epochs. So this is what a simple pruning modifier or simple pruning recipe will look like. Jumping to quantization, what a simple quantization recipe looks like. So again, we have our modifiers. And this is the quantization modifier. It's really simple. You just give it a start epoch when you want to start quantizing. And then there's a few things under there, which is freezing batch norm stats. So technically what's happening on the quantization modifier is that whenever you have a convolutional neural network, you're going to do convolution followed by batch norm followed by an activation. The batch norm and the convolution are going to get folded at inference time. So what you want to do is eventually freeze those batch norm stats. So you can actually do that folding, and that way you can update both the convolution and the batch norm together as it would be running an inference, where we fold those. All right, great. So that, and then finally putting these together, pruning plus quantization recipe. So we have our modifiers defined here. We have a global magnitude pruning modifier from earlier. We have our learning rate modifiers that control the learning rate for the while we're pruning. And then we're going to add on our quantization modifier at epoch 50. We're going to set a smaller learning rate for quantization. Generally, you can think of it as whenever we're quantizing a model, we've already reached a solution and we don't want to deviate from that solution. So we set a really small learning rate generally when we're quantizing, just so that we can adjust the weights a little bit and we don't want to retrain completely and completely jump from our trained solution. And then we're just going to quantize for 5 training epochs. So we're going to run quantization aware training for 5 epochs. So you can see how we bumped up to 55. And yeah, so that's how this is a simple recipe that does sparse pruning plus quantization to create a sparse quantized network. To apply that recipe, we can then use that in any of our sparse melt commands, or we can do a custom integration, which is what I'll end with and run through.
So Mark, I have a quick question in this.
Yeah.
So we also define these. So these the configuration that you showed just before. These becomes like a kind of hyperparameter for sparsification now. So
Yeah.
so like again like this is again like in the getting the sparsity right for our model. Is this again kind of if like let me rephrase, like how wrong would I be on a scale of 1 to 10 when I say sparsity is also like hyperparameters is in sparsity are again another layer of experimentation?
Yes, you're completely right in saying that, and that is what gets added on. That's why we generally recommend the sparse transfer pathway, so you don't have to go through this this additional hyperparameter exploration. Because what we'll do internally at Neural Magic is we'll do all this hyperparameter exploration, make sure we get the right hyperparams, and then create that general sparse architecture so you can just plug it in. And that's generally why we recommend sparse transfer. Once you go into sparsifying a model, it does become more complicated, and that's where you have to iterate over hyperparameters. We're actually in not by the end of this year, but within very soon into next year in Q1, we're going to be pushing out a UI that handles all of this. So it can give you suggestions for the hyperparameters, help you iterate through those hyperparameters. And we do have an alpha version of it that we created, I think, about a year and a half back that works okay. It's called Sparsify. And it tries to approximate what some of these hyperparameters should be. But this is where a big focus item is actually right now, to make this hyperparameter exploration much simpler by doing intelligent starting values and then recommending new values for you so that you don't have to go through to hopefully limit how much experimentation you have to do.
A quick follow-up question on the same topic, like when you say like we recommend like to use the transfer kind of learning for sparsity, but doesn't that restrict it to a specific like model or like a set of models, like vision models? Like okay, there are like 10 kinds of architecture, and it may be highly possible or it may not be possible, like to transfer a sparsified model in one kind of model to transfer the sparsity to another set of another model in the same family. And like is it possible or is it not possible, or is it where it becomes a kind of a conjecture, like you have to sparsify and your set of transfer learning techniques only works for like a given set of architecture, like autoencoders, NLP models, transformer models, then kind of like diffusion models, and so on and so forth.
Yeah. So okay. Yeah.
So yeah, I mean, so the question is like, does the library, the technique given in the deep sparse libraries works on point-to-point, model-to-model kind of things, or like for a set of families of models?
Yeah. So when we're doing sparse transfer, you're absolutely right. We are limited in architectures. Those are going to be ones that are pre-sparsified. We're not able to transfer the sparsity pattern between models. What we're doing is, you're taking models that we've already pushed up to the sparse zoo, so architectures that we already have, So this is like ResNet 50 or YOLO v5L or BERT large, things like that, right? So you are limited whenever you're doing sparse transfer to use cases that we've already solved to be able to leverage. So all of that, essentially what sparse transfer, all that it's doing is it's taking that pre-sparsified architecture, freezing the sparsity maps across them so that you can continue training the weights that aren't sparse. So we're just freezing the mask rather than freezing the weights, and then the weights continue to update for a new data set, essentially. So we're not able to transfer it across different architectures or even models in the same family. So if you're trying to, if there is a model that you want sparsified, either because it's not a use case we've sparsified yet, or because it's an architecture that you already have, or an architecture you think is going to be better, then you need to go down the sparsified model path.
All right. Okay.
Yep.
Thanks.
Yeah, definitely. Great question. Okay, great. And then so custom integrations, and this gets into additionally along those lines of architectures that we've already sparsified. For all those architectures and use cases, we're pushing up already integrated code, so you can just run some CLIs or plug in the Python APIs that we've integrated with. So for example, we're integrated with Hugging Face transformers, so you can just use those out of the box. Integrated with Ultralytics, YOLO v5 for object detection, so you can just use those out of the box. Where if there is something new that that you want to use, a new architecture or a new use case, generally you're going to have to create a custom integration for sparsifying those models as well. So this means if you're using, if you're trying to do pose detection, which is something that we're starting to work on now, but you want to use it now, then you're going to have to go through and integrate SparseML into that training code so you can use recipes. And that's what this walks through. So we want to integrate SparseML. And this walks through everything that happens to be able to do the integration. What we're going to do is import the scheduled modifier manager from SparseML. This is going to be our instantiation of the recipe. So the recipe that we defined, this is how we get it loaded into code. And then we're going to modify the model and the optimizer. So this is how we actually take over the training graph. Underneath the hood, what we're doing is we're holding on to a reference to the model as well as the optimizer, and we're overriding the optimizer step function. So the optimizer step will happen, but we run code both before and after the optimizer step, so we can apply things like sparsity to the model, or regularization, or quantization, things like that. So this is how we make it simple so that you don't have to build out all these, you don't have to redefine your network to be able to do quantization or put a bunch of code to figure out when to prune. This is all the code that you need to plug in, and this works with the most complicated and both simple and the most complicated training scripts that you can come up with, at least on the PyTorch side. We have limited support on TensorFlow and Keras, so we definitely recommend going down PyTorch. PyTorch has also just been significantly easier in our experience to work with. But yeah, so you'll plug in these 3 lines and then run your typical training code and then finalize the model. So what this looks like in practice, just giving a simple training example. This is pulled from, or this is a simplified version of just training a image classification model. So we'll walk through it line by line. We're going to import everything we need from PyTorch to do. So we have a data loader, our loss function using SGD optimizer. From SparseML, we're going to be using a ResNet 50 model that we have defined in there, and then also an ImageNet with 2T's data set. This is a smaller version than ImageNet to iterate on. It only has 10 of the classes from the 1,000 classes in ImageNet, and also downscales the size of them. So much faster to iterate through and get a classification model to show off. And big thing is we're going to import that schedule modifier manager that I said. So we define that there are 10 classes. We create our ResNet 50 model for 10 classes. This is going to create the architecture as well as instantiate it with default weights. We're going to set our batch size to 64 for training. So we're going to create a trained data set and a data loader to load in that data as we're training. And that we're going to create with batch size 64. We're going to tell it that we want to train on CUDA if it's available. Otherwise, we use the CPU. And then we're going to put the model onto that device. So if we are training on GPU, we're going to put that model onto the GPU. So this is all just standard training code here. And other than, where is it? This line here. So standard training code, we create our optimizer using our model, And then all that we're going to do is override that optimizer using our manager.modify call. After this is all just standard training loop, right? We're going to go through each epoch, run through it, and then track our losses, and then just iterate through each batch and until we get convergence and then finalize. So really simple, again, just highlighting, importing the modifier manager, creating the manager from the recipe that you defined. And then right after you create your optimizer, just add in this line to do a manager.modify, and that will wrap up the integration that you need to do for SparseML. And now you can prune, quantize, do whatever you want with those models using recipes. All right. And yeah, and that's everything I wanted to run through. Any other questions that came in? All right, great. Well, I will end it there then. Thank you guys. And yeah, if anyone has any questions, feel free to reach out. You can reach out on LinkedIn. We also have a community Slack available. Just go to neuralmagic.com and you'll see our Slack link. So you can also join there to ask questions as well to get support. Yeah, hopefully everybody enjoyed that. Let me know if you have any questions and enjoy the rest of the hack event. Thank you, everyone.
Thanks, Mark. It was really nice sessions and really interesting speech on sparsity in deep learning, really hot topic. And I hope you might have gone through the Torsten Hoffler sparsity paper, the 90-page long paper. Yeah, really interesting stuff. And so good to see some of the stuff you guys are also incorporating, the second order sparsity, the first order sparsity.
Yeah.
We are also leveraging it in our biomedical imaging research that we have.
Nice.
Rare optimizations for COVID-19 chest enhancements. So we'll use your library for that also. And
awesome. Yeah.
Speed up.
Yeah, definitely.
Sure,
awesome.
Sure. All right. Thanks, Mark. If anybody has any questions, please feel free to reach out to Mark here, LinkedIn, Slack, anywhere. That's fine. And don't forget, we have given access to everybody for the Infer cluster that has Volta 100 cards, 4 cards per node, more than 80 nodes on that cluster. So you guys are more than welcome to explore Volta generation of cards. And if you guys need Ampere generation, we have DGX Superpod at Virginia Tech Advanced Research Computing. That gives 240 compute hours on a GPU per node. Feel free to use that as well. All right. Thanks a lot, Mark. We appreciate your time on Halloween weekend, and good to see folks still joining a little too late for now. But anyway, thanks, Mark. Thanks, everyone. Have a great Halloween weekend and an afternoon and an evening or a night if you are in other time zone.
Awesome. Thanks, Ayush.
Thanks, Mark.